These are the notes for AP Calculus on the topic of local linear approximation, or another way of saying that, using the tangent line to approximate the value of a function. So what this basically consists of is using the tangent line to approximate the value of a function at points that are close to the point of tangency. So let's say this is our function graphed right here. Then let's say we've got a point of tangency right there. And got a tangent line like that. Let's try that again here. There we go. Okay, so that's our tangent line. And what this means is that's the linear part, because the tangent line is linear, it's just a straight line. And notice it's called local linear approximation. Local means close or nearby. So close to the point of tangency there, you can see the tangent line is pretty close to where the function is. As we get further away from it, it's not as likely to be as close. But right in there, but close to the point of tangency, it is pretty close. So it can be used as a decent approximation of where the function is at. Now if you notice, this one, the tangent line, lies above the graph. So if you use this tangent line to approximate the function, it would actually overestimate the value of the function. However, let's say instead our function looked like this. The graph of the function was like this, and let's say the point of tangency was right there. And then we had our tangent line, something like that. So now if we look locally or close by our point of tangency, you can see here, now the tangent line lies below the graph. And that would mean that this tangent line would underestimate the actual value of the function. And what's causing that, the difference between the two graphs here, is this first graph is concave down, shaped like a frown, and the second graph is concave up, shaped like a cup. So it's due to the concavity that it underestimates it. So it overestimates it when the graph is concave down, and the tangent line will underestimate the actual value when it's concave up. And remember, concavity comes from the second derivative. So the second derivative will determine whether the tangent line under or overestimates the actual function. Because notice, no matter where I draw the tangent line here, if it's concave down, the tangent line is always above the graph. And same thing if it's concave up, no matter where I draw the tangent line, it's always below the graph. Okay, let's look at some specific examples now. This one says the function f is twice differentiable with f of 3 equals 2, f prime of 3 equals 5, and f double prime of 3 equal to negative 4. It says what is the value of the approximation of f of 2.9 using the line tangent to the graph at x equals 3. And then it asks, is this approximation greater than or less than the actual value of f of 2.9? And give a reason for your answer. Okay, so first thing we need, it says using the tangent line, or the line tangent to the graph at x equals 3. So first we need to find that tangent line. So remember, the two things you need for the tangent line are, to write the equation of the tangent line, are the point of tangency and the slope. And if you look at the information you're given right here, we want to find the point at x equals 3. It gives us f of 3 is 2, which is another way of writing the point 3, 2. There's our point of tangency. And then the other thing we need is the slope, but it tells us right here that f prime of 3, remember the derivative is giving you the slope of the function, or the slope of the tangent line, is 5. So 5 is our slope. So those are the two things we need to do to write down our tangent line. Okay. So the equation of the tangent line would be y minus the y-coordinate 2 equals the slope 5 times x minus the x-coordinate 3. So that's in point slope form. Now, if that's all we're interested in, the tangent line, you could actually just leave it like that. But we're actually going to use the tangent line for something in this case. And what we're going to use it for is to approximate f of 2.9. So the way you do that is you just take 2.9 and substitute in for x right there. And notice 2.9 is close to our point of tangency at 3. So that will mean it will be a decent approximation. That's the local part. They wouldn't ask you to estimate if it was like f of 7 or something, which is really far away from 3. So let's plug that in and see, substitute that in and see what we get. So y minus 2 equals 5 times, let me substitute that in for x, so we get 2.9 minus 3. And just simplify that. So we'll get y minus 2 equals 5 times 2.9 minus 3 is negative 0.1 times the 5 gives you negative 0.5. And finally, we just solve it for y to figure out the y-coordinate on the tangent line when x is 2.9. So just add the 2. And we get y equals 2 minus 0.5 is 1.5. So 1.5, that's the actual point on the tangent line, which is an approximation for where the function's at 2.9. So now we can say f of 2.9 is approximately equal to 1.5. That's the first thing. What's the value of the approximation of f of 2.9 using the tangent line at x equals 3? There it is. Okay. Now, the second part of this question says, is this approximation we just found here greater than or less than the actual value of f of 2.9? So remember, we figured out that whether the tangent line under or overestimates the function is all based on the concavity. And the concavity comes from the second derivative. So let's see what we know about the second derivative. So notice it tells us right here, the second derivative, f prime double prime of 3 equals negative 4. Since the second derivative is negative, that means our graph is concave down. So if it's concave down, shaped like a funnel, it looks like this. And that means our tangent line lies above the graph. So you can see right here the tangent line's above where the function is, so that means it's overestimating. So we can say f of 2.9 approximately equal to 1.5 overestimates f of 2.9, or you can say the actual value of f of 2.9. And then your reason for your answer would be since f double prime of 3 is less than 0. Okay, because that's what makes it concave down at the point of tangency. Okay, let's take a look at another example. This one says that y equals f of x be a particular solution to the differential equation dy dx equals xy squared with f of 1 equal to negative 2. So there's two parts to this one. Its first Part A says write an equation for the line tangent to the graph of y equals f of x at x equals 1. So again, the two things we need for the tangent line are the point of tangency and the slope. Again, right here, f of 1 equals -2. We want the tangent line at x equals 1, so 1, -2, there's our point of tangency. But this time we don't have the slope. However, they do give us the derivative right here, dy dx. So all we have to do to find the slope specifically at our point of tangency is substitute that point in. So the derivative specifically when x is 1 and y is -2 would equal x, which is 1, times y, which is -2 squared. And when you simplify that, -2 squared is 4 times 1 gives you 4. So there's the slope of our tangent line. So our tangent line at x equals 1 would just be, again, in point slope form, y minus the y coordinate is -2. So minus a -2 makes it +2 equals the slope, which is 4, times x minus the x coordinate, which is 1. So that's the answer for part A. There's our tangent line at x equals 1. And then part B says use the tangent line from part A to approximate f of 1.1. And then is this approximation for f of 1.1 greater than or less than f of 1.1? And explain your reasoning. So again, all you have to do is substitute in 1.1 in for x in our tangent line to see what we get. So when we do that, we'll get y plus 2 equals 4 times 1.1 minus 1. So 1.1 minus 1 gives you 0.1. 0.1 times 4 gives you 0.4. And then just subtract the 2. So we end up with y equals -1.6. So our approximation here, f of 1.1 is approximately equal to -1.6. So again, this is the exact point of the tangent line, which is an approximation for where the function is at. Because remember, this is local, right? 1.1 is close to 1, so the tangent line should give us a decent approximation there. And then is this approximation for f of 1.1 greater than or less than f of 1.1? So again, that's due to the concavity, whether it under or overestimates it. And the concavity comes from the second derivative. So we don't have the second derivative at all on this one, but we do have the first derivative right here. So let's go ahead and take the derivative of the first derivative using implicit differentiation. So the derivative of the first derivative, that gives us the second derivative, which is written d squared y dx squared. And then to take the derivative of xy squared, that's where we need to use the product rule, because we've got x times y squared. So using the product rule, we take the derivative of the first one, derivative of x is just 1, times the second one, y squared as it is, plus the first one, x as it is, times the derivative of y squared is 2y, but because the y doesn't match up with the x here, that's where we need to multiply it by dy dx. And then all you have to do is just substitute in the first derivative right there. We know what the first derivative is. It's xy squared. So if we simplify this, we get the second derivative equals y plus 2xy times xy squared. So we get second derivative equals y plus 2x squared y cubed. And again, we want to figure out is, oops, this is y squared, sorry. Is the second derivative positive or negative at our point of tangency? So let's go ahead and substitute those in. So the second derivative, specifically when x equals 1 and y equals negative 2. So that'll give us y negative 2 squared plus 2 times x is 1 squared times negative 2 cubed. So negative 2 squared gives you 4. Negative 2 cubed is negative 8 times 1 times 2 gives you negative 16. So we get negative 12. And again, since it's negative, second derivative, that means the graph is concave down, shaped like a fountain. And if it's concave down, that means the tangent line is going to, again, overestimate the actual value. So we can say f of 1.1 approximately equal to negative 1.6 is greater than f of 1.1. And it says to explain your reasoning. So again, that would be since we just figured out the second derivative specifically when x is 1 and y is negative 2 is less than 0. So really our justification is just like the one over here, except it's got a different notation. Here we had f double prime of 3 is less than 0, and here it's written in this notation, the second derivative at this point is less than 0. Okay. Let's take a look at some more examples. This one says the function g is defined for when x is greater than 0, with g of pi equal to negative 2 and g prime equal to sine of 2x over 3 squared. Write an equation again for part A for the tangent line at x equals pi. So again, we're given g of pi is negative 2. So that means pi negative 2 is our point of tangency. And we need to find the slope to write the tangent line. So we've got the sine of 2x over 3 squared. Let's just rewrite that so it's easier to take the derivative. Really, this is the same as g double prime of x equals, well, sine is being squared. So and inside of sine, we've got, instead of 2x over 3, that's the same as 2/3 x. When you take the derivative, it's really the double chain rule here, because we've got sine inside the square there and 2/3 x inside of sine. So when you find the second derivative, g double prime of x, start on the outside and work your way in. So you take the derivative outside using the power rule, so that would be 2 sine of 2/3 x. Now it's just to the first power, times the derivative of sine is cosine, times the derivative of the innermost function, 2/3 x, is just 2/3. So I really like this 2/3 x instead of 2x over 3, so you'd see you actually don't need the quotient rule there. And now we can substitute in pi. Oh, let's see, the second derivative here we don't need until part B. Sorry about that. So we'll do that right here. Here we just needed the tangent line. Sorry, I got a little ahead of myself here. So for this one, since this is already the first derivative, all we have to do is plug in pi to get our slope. So that'd be sine of 2 pi over 3 squared. So 2 pi over 3, right over here, in the second quadrant. So the interior angle here is pi over 3, so this side is root 3, and this is 2. So that would be, sine is the opposite of right hypotenuse, so it would be the square root of 3 over 2 squared. When you square that, square root of 3 squared is 3 over 2 squared is 4. So there's our slope. So the tangent line in part A would be y minus the y coordinate, so minus -2 makes it plus 2, equals, we just figured out the slope is 3/4, times x minus the x coordinate pi. Now we can use the second derivative here to figure out part B, because it says, does the tangent line lie above, or at x equals pi, lie above or below the graph for when x is between pi and 3.2? So right there by our point of tangency and y. So to see if the tangent line lies above or below, again, that's due to the concavity. So here's our second derivative we already found here. So then all we have to do is substitute in pi into that, and to see if it's positive or negative. So all we have to really do is to see if it's positive or negative. So over here, when you plug in, well, I'll just plug it in here so you can see what we're doing here. So it'd be 2 times the sine of 2 pi over 3 times the cosine of 2 pi over 3 times 2/3. So the sine of 2 pi over 3, we can see here, we already figured out it's radical 3 over 2, it's positive, times the cosine of 2 pi over 3, this would be -1, so it would be -1/2, so that would be negative. So we don't need the actual value here. Just need to know whether it's positive or negative. So positive times a negative is negative. So since the second derivative is negative, then we know the graph is concave down. And since it's concave down, we know the tangent line lies above the graph. Okay, so we can say the tangent line lies above the graph, since g double prime of pi is less than 0. As it said of y, so there's our justification. Okay, let's take a look at another example here. This one gives us a table of values. It gives us first row is x, second row h of x, and third row h prime of x. So it says let h be a function that's twice differentiable for all real numbers. In other words, you can just take the derivative twice everywhere. And the table above gives values of h at selected points in the closed interval from 1 to 10. And then it says suppose h double prime of x is less than 0 for all real numbers. So for part A, it says use the tangent line to the graph of h at x equals 7 to show that h of 8 is less than 5. So first we need the tangent line at x equals 7. So again, we need two things, the point of tangency and the slope. So when x is 7, here we use our table, and we can see the y coordinate is 6. So 7, 6 is the point of tangency. And we need the slope. Well, the slope is our derivative here. So when x is 7, h prime of x, so the derivative of the slope, equals -1. So there's our slope. So our tangent line y minus y coordinate 6 equals negative 1 times x minus the x coordinate 7. And we want to show that h of 8 is less than 5. So a little bit different here. So 8 again is close to 7, so we can use it as an approximation here. So if you plug in 8 there, that'll be y minus 6 equals negative 1 times 8 minus 7. Which will be y minus 6 equals 8 minus 7 is 1 times negative 1, gives you negative 1. And then if you add the 6 over, we get y equals 5. And notice here it says less than 5. Well, it's less than 5 because it tells us right here the concavity, it's concave down, so the second derivative is less than 0 for all real numbers. So if the graph is concave down, like that, and we've got our tangent line right here. Now this would be our approximation for h of 8 would be 5, but this is showing that the actual value of h of 8 would have to be less than 5, which is true because the tangent line overestimates it. So that's showing the work there, and we can just say h of 8 is less than 5, since h double prime of x is less than 0. And then part B says use the secant line for the graph on the interval 3 to 10 to show that h of 8 is greater than 30 over 7. So remember the secant line is, instead of the tangent line where it touches the graph at one point there, the secant line goes through 2 points on the graph. So from 3 to 10, notice our point of tangency 7 is right in the middle of that. So from 3 to 10, that would be the secant line. This one was our tangent line. So first we need the equation for the secant line. So again, we need two things, a point and the slope. So from 3 to 10, since it goes through those 2 points at 3 and 10, then we can use those points to get our slope. So notice we have the point 3, 5, and 10, 4. So using the secant line on that interval from 3 to 10, this point is 3, 5, this is 10, 4. So the slope would be the difference of the y's, so 4 minus 5 over the difference of the x's, 10 minus 3. So that gives you negative 1 over 7. So there's your slope of your tangent line, so your secant line. And to write the secant line, we can use either one of these points. I'll use 3, 5, the numbers are just a little bit smaller, so I'll say y minus the y coordinate here, 5, equals the slope we just figured out, negative 1/7, times x minus the x coordinate, that point is 3. And again, we're using it to approximate h of 8, so let's plug in 8 there, see where that point is on the secant line. That'll give us y minus 5 equals negative 1/7 times 8 minus 3. So you get y minus 5. 8 minus 3 is 5 times negative 1/7, gives you a negative 5/7. And then if you add the 5, that's like adding 35/7. So 35/7 minus 5/7 gives you 30/7, which not coincidentally is the value they have right here. So notice here, because it's concave down, the secant line is underestimating where the function is. If it was concave up, it would be the reverse. So we can say h of 8 is greater than 30 over 7, since we know that's an underestimate of it. The actual value is greater than it. And it would be, since, again, due to the concavity, h double prime of x is less than 0. So what we really found in this is a range for where h of 8 would have to be between. Due to the tangent line, a tangent line overestimated, so it has to be less than 5. And due to the secant line with 30 over 7, which underestimated it, so that would have to be greater than 30 over 7, which is like 4 and 2/7, if you make it a mixed number here. So in other words, we know that the actual value of h of 8 is somewhere between 5 and 4 and 2/7. So we have a pretty small range there of where h of 8 would have to be between. All right, let's take a look at an applied problem now. It says at the beginning of 2011, a landfill contained 1,000 tons of solid waste. The increasing function w models the total amount of solid waste stored in the landfill. Planners estimate that w will satisfy the differential equation. dw dt is 1/20th w minus 600 for the next 30 years. W is measured in tons and t is measured in years from the start of 2011. So part A says use the tangent line to the graph of w at t equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 4 months of 2011, time 1/3. So there's a lot in there. Let's start with what, use the tangent line to the graph of w at t equals 0. So again, the two things we need for the tangent line are the point of tangency and the slope. So on the previous problems, we just would have points of tangency that are x, y. But in this problem, there's no x and there's y, there's w and there's t instead. So in this problem, instead of x, if you look right here at our dw dt, normally this would be the dx there. So t is like our x, and normally this would be a y right there. And so the w is in the place of the y. So our point of tangency on this one, to read it carefully, it says t is measured in years from the start of 2011. So in other words, the start of 2011 is t equals 0, and that's when we want the tangent line at t equals 0. And note, if you read the very first sentence, at the beginning or start of 2011, a landfill contains 1,000 tons of solid waste. So there's our point of tangency right there. At time 0, we know there's w is 1,000. So w is measured in tons. There it is, 1,000 tons. So the other thing we need is our slope. And the slope comes from right here. Here's the derivative. So dw dt, specifically, when normally you'd say t equals 0 and w equals 1,000, but notice there's no t in our derivative here. So that's what makes it a little different. When w is 1,000, now, excuse me, it'd be 1/20 times 1,000 minus 600. So if we just simplify that, we get 1/20 times 1,000 minus 600 is 400. Divided by 20 there gives you 20. So there's our slope. So the tangent line here would be, normally it's y, but here it's w, so it would be w minus the w coordinate, 1,000, equals the slope, 20, times normally the x minus the x coordinate, but here it's t, so it would be 20 times t minus 0, which is just the same as t. So there's your tangent line, and then we want to use it to approximate the amount of solid waste that the landfill contains at the end of the first 4 months. It gives you a hint, it's time 1/3. Because 4 months is 1/3 of a year, because there's 12 months in a year. So then you would just substitute in a 1/3 right there. So you get w minus 1,000 equals 20 times 1/3. So that's 20/3. And then just add 1,000, which is the same as, if you get a common number, adding 3,000 thirds. So we get w equals 3,020 thirds. And in this case, W, the units for it, is measured in tons of solid waste here. So that's our estimate from part A. And then in part B, it says find the second derivative in terms of W. So we had our first derivative here. Only thing I'm going to do here to make it easier to find the second derivative, I'm actually just going to distribute out that 1 over 20 to both of those. So the first derivative, dw dt, is 1 over 20 w, and then 1 over 20 times negative 600 would be negative. 20 goes into 630 times, so minus 30. And then find the derivative of that to get to the second derivative. So that would be the second derivative, t squared w dt squared, equals derivative of 1 over 20th. W would just be 1 over 20 dw dt. The derivative of 30 is just 0. And then to get rid of the dw dt here, well, we have dw dt, so we just substitute that in right there. So the second derivative is 1 over 20 times 1 over 20 w minus 30. And then all we have to do is figure out when w is 1,000 whether this is positive or negative. So the second derivative, specifically when w is 1,000, will be 1 over 20 times 1 over 20 times 1,000 minus 30. So you'd have 1 over 20. 1,000 divided by 20 is 50 minus 30. So you can see that's 20 over 20, that's just 1, so it is positive. So this one, since the second derivative is positive, the graph would be concave up. And if the graph is concave up, then that means the tangent line is below the graph. In other words, it underestimates it. So our estimate here, which was 3,020 over 3, say 3,020 over 3 tons, underestimates the amount of solid waste at t equals 1/3, since, and the reason here would be our second derivative, when w equals 1,000, this time turned out to be positive or greater than 0. And that concludes the notes on the topic of local linear approximation, using the tangent line to approximate the value of a function.